in this segment, we are going to discuss a very important topic, which is the anion gap. And we're going to learn how to calculate the anion gap. And let me tell you first that the anion gap is a purely metabolic acidosis business. So the anion gap, we will not have to calculate the anion gap in acid-base problems unless we have metabolic acidosis as a primary diagnosis or a secondary diagnosis. Again, I repeat, we do not need to calculate the anion gap in an arterial blood gas analysis unless one of the primary diagnoses or the secondary diagnosis is metabolic acidosis. In this case, we will have to calculate the anion gap in order to define what type of metabolic acidosis we have. Because as we are going to discuss shortly, we have two types of metabolic acidosis. One type elevates and increases the anion gap, and the other type does not result in elevated anion gap. So let's start the discussion from its very beginning, and let me use the whiteboard for that. So the body has positively charged ions, and we call them cations. And also it has negatively charged ions, and we call these negatively charged ions, we call them anions. And normally in the human body, the cations should equal the anions, so that we are electrically neutral. And there are many panels, there are many tests that can measure the body cations and the body anions. And one of these chemistry panels is this famous fishbone, or Chem7. And Chem7 measures the sodium and potassium, and these are cations, and it also measures the chloride and bicarbonate, which are anions. So the first column is actually cations, and the second column of Chem7 is actually anions. And here we have glucose, here we have BUN and creatinine. Okay. So the cations include the measured cations as measured in Chem7, the sodium and potassium. But are these the only cations that we have in the human body? Of course not. We have a lot of other positively charged ions. We have magnesium, it's positively charged. We have some plasma proteins are positively charged. So the cations will include the measured cations and the unmeasured cations. And by the same token, the anions include the measured anions, which are measured in Chem7, chloride and bicarbonate, and also we have a lot of unmeasured anions. The most important unmeasured anion, it's unmeasured in Chem7, it's unmeasured in this fishbone panel. The most important unmeasured anion is albumin. Albumin is negatively charged. And these two should equal each other, should be equal. So let's make a simple trick. Let's move the measured anions to this side of the equation, and move the unmeasured cations to the opposite side. And we learn that once you cross the equal sign, you should acquire a different, or you should acquire the opposite sign. So when we rewrite the equation, it's going to be rewritten as follows. Measured cations minus measured anions, because now measured anions moved from the other side, so it should acquire a different sign, equals what? Equals the unmeasured anions minus the unmeasured cations. Scientists agreed that we are going to call this part measured cations minus measured anions, which is the first column in Chem 7 minus the second column. We are going to call this the anion gap. The anion gap. And what are the unmeasured cations? Unmeasured cations include magnesium, include calcium, and this includes aluminum, zinc, and actually these do not play a significant role in the acid-base problems. So we are going to just keep the unmeasured anions. And therefore, theoretically, the anion gap is a way to estimate the unmeasured anions. The anion gap is a way to estimate the unmeasured anions. The anion gap is a way to estimate the unmeasured anions. So how to calculate the anion gap? It's the first column minus the second column. Let's put some numbers here. Sodium is 140. Potassium is 4. Chloride is 104. And bicarbonate is 24. So the anion gap is the first column minus the second column. The first column is the 140 of sodium plus the 4 of potassium, should be 144. You notice that potassium is very, very tiny. And this 4, even if it increases to 5, 6, 7, it is still the smallest number. So most protocols ignore considering potassium in the calculation of the anion gap. So now the first column will only be the sodium, So to calculate the anion gap, it's sodium minus the sum of chloride and bicarbonate. So the anion gap is, it's 140. That's the first column, that's sodium, minus the sum of 104 plus 24. So the anion gap is 140 minus 128. So the anion gap is 12. And that's the normal anion gap. Notice that this 12 does not mean that we have the anions less than the cations by 12. But we know that in the human body, the cations equal the anions, but the gap is the unmeasured anions. And we know already that this unmeasured anion is nothing but the albumin. So normally, the anion gap, which is 12, it tells us that we know that we have equal amounts of cations and anions in the body, and this gap of anions, which is the 12, is nothing but the albumin that we do not measure in this CAM7 panel or this fishbone panel. So the anion gap is a way to estimate the unmeasured anions. So the anion gap normally is 12. Normally is 12. What can go wrong with the anion gap? In some types of metabolic acidosis, the anion gap is elevated. In some types of metabolic acidosis, the anion gap is elevated. Now, metabolic acidosis means what? There are too much acids in the circulation. Too much acid in the extracellular fluid. Now, Chemistry 101 tells us that an acid is any substance that is capable of liberating hydrogen ion. So if this is an acid molecule, when it liberates a hydrogen ion, and this hydrogen ion will be buffered by bicarbonate. So bicarbonate will take care of this hydrogen ion. This particle that remains will be negatively charged, correct? This particle will be negatively charged. So what do we call this particle? We call it anion. So anions come from acids. Anions come from acids. Unmeasured anions come from acids. So the normal anion gap tells us that the unmeasured anions, the 12 unmeasured anions, come from albumin. But if you have elevated anion gap, more than 12, higher than 12, this tells us that we have pathologic unmeasured anions that must have come from pathologic acids added to the system, to the body, to the circulation. So once we have elevated anion gap, we know that we have that type of metabolic acidosis where there are pathologic acids added to the circulation. Let me explain this again. Let me start now by explaining the two types of metabolic acidosis. The two types of metabolic acidosis. To begin with, metabolic acidosis. In metabolic acidosis, what do we have? We have low pH. We have low pH and low bicarbonate. Bicarbonate in metabolic acidosis is less than 24. In metabolic acidosis, bicarbonate is less than 24. And this causes the pH to become less than 7.4. Now, there are two ways to lower the bicarbonate content of the body. There are two ways to lower the bicarbonate content of the body. And therefore, there are two types of metabolic acidosis. Let me give you this example. Let's say I have with me 24 quarters. I have 24 quarters. So let's say every morning I leave my house with 24 quarters in my pocket. There are two ways to lower this amount of 24 coins that I have. Either I drive through Starbucks and I use some of these quarters to purchase coffee. So that's the first method, use it. So if I use some of the coins, I'm gonna lower the amount of coins that I have, and it will be less than 24 quarters. Or maybe as I put some quarters in my pocket, I might lose some, and that's another way to lower this 24 coin amount. So the two ways to lower the bicarbonate content of the body is use it or lose it. Use it or lose it. These are the two ways of lowering the bicarbonate amount in the body. And these are the two types of metabolic acidosis. Lose it as in what? Simply as in diarrhea. Lose it as in diarrhea. If we have diarrhea, we simply lose bicarbonate going to the toilet. Another conditions where we lose bicarbonate is Addison's disease, that we will discuss in endocrinology, and a renal condition known as renal tubular acidosis. In these three types, the anion gap is not elevated. The anion gap is not elevated. So we call this type of metabolic acidosis, we call it non-anion gap metabolic acidosis. Non-anion gap metabolic acidosis. Because the anion gap is not more than 12. The anion gap in diarrhea, Addison's disease, renal tubular acidosis, when you calculate the anion gap, when you do your calculations, it's sodium minus the sum of chloride and bicarbonate, you will find it 12. So it's not elevated. It's non-anion gap metabolic acidosis. So in the test, if I ask you, give me examples of non-anion gap metabolic acidosis, the answer will be diarrhea, Addison's disease, renal tubular acidosis. The other type of metabolic acidosis is that type of metabolic acidosis where you lower your bicarbonate because you use it. What do we use bicarbonate for? We use bicarbonate to buffer acids. And when you buffer an acid, and this acid liberates hydrogen ion, and this hydrogen will be buffered by bicarbonate, and this lowers the amount of bicarbonate, which is metabolic acidosis. And what accumulates in the circulation after you buffer pathologic acids? What accumulates in the circulation? What will accumulate will be unmeasured anions. Why unmeasured? Because the anions that we measure are chloride and bicarbonate. These are the anions that we measure in CAM7 or fishbone. So what will accumulate in the circulation will be unmeasured anions. And in this case, the anion gap will be more than 12. because the anion gap measures the unmeasured anions, and these unmeasured anions accumulate in the circulation because they are coming from these pathologic acids that bicarbonate was consumed in buffering them. And we call this type of metabolic acidosis, we call it anion gap metabolic acidosis. And the conditions that cause anion gap metabolic acidosis are so important that there is a very famous mnemonic for these conditions, which is a cult. A cult. And let me use a special screen for this A cult. What are the A cult conditions? The A stands for aspirin toxicity or intoxication. The A stands for aspirin. The K stands for ketosis. As in DKA. Keto acids accumulation in the circulation. The U stands for uremia. Renal failure. The L stands for lactic acidosis. And finally, the T stands for some toxins. Toxins like methanol, ethanol, and ethylene glycol. What is common among all these occult conditions? What is the common factor among all of them? In all of them, there is accumulation of pathologic acids. All of them represent conditions where some pathologic acids, acids that do not physiologically exist in the body, that do not normally exist in the body, for disease conditions, for pathological reasons, they accumulate in the body. Like what? Aspirin toxicity. What's the acid here? It's acetyl salicylic acid. So there is accumulation. Someone ingests a whole bottle of aspirin. That's a lot of acetyl salicylic acid in the circulation. In DKA, what are the acids? Acetoacetic acid. Acetoacetic acid. Beta hydroxy butyric acid. These are keto acids accumulating in the circulation. Uremia, all types of pathologic acids, because the kidney is sick, unable to get rid of acids. Here, what do we have? Lactic acid. In cases of hypovolemic shock, septic shock, and tissues are obliged to metabolize anaerobically, a lot of lactic acid accumulates in the circulation. In toxins, all these methanol, ethylene, ethanol, ethylene glycol, all these are acids. So in a cult, there are pathologic acids accumulating in the circulation. Acids. And when these acids liberate their hydrogen, and the hydrogen is buffered by bicarbonate, what accumulates in the circulation will be anions. What accumulates in the circulation will be anions. will be the negatively charged particle that was left. And these anions are unmeasured anions. And therefore, the anion gap will be more than 12. So we know that the 12 comes from albumin, and what is more than that comes from these pathologic acids. And this is the second type of metabolic acidosis, the anion gap metabolic acidosis. And this ends this segment here. And in the coming segment,